Hi guys, in today's video we're going to be looking at extended bodies in equilibrium. So we're going to focus on the conditions that are necessary for that to be the case. So the way these problems will tend to play out is you'll be given an object which is extended in space, and you'll be either told that it's in rest or you'll sort of be able to infer from the problem that this object is at rest. And once you know that it is at rest, we can say two things about the system, and one is it has no linear acceleration, otherwise it's moving. But also now we can say it should have no rotation. So these give us two conditions which we can impose on the system, and from there we can solve for some quantities that we'll be interested in. So our first condition is really our linear condition. And so we'll recall this just amounts to the fact that if there's no acceleration, that means the sum of the forces should be equal to 0. So this is true in the x and the y direction. So oftentimes we'll really get two conditions here. One, the sum of the forces in the x is 0, and then two, that the sum of the forces in the y is also 0. So this is something we've done before. This is really nothing new here. But now that we've done some rotation work, we can actually add in our second condition, which is our rotational condition. And this basically tells us that the sum of the torques must also be 0. And so we can recall that a torque here is going to basically mean that we have an angular acceleration, right? If we have a net torque, this will be equal to I alpha. This is one equation that we have for torque. So if there's a torque present, that means there's also an angular acceleration present, which means that there's some rotation. And so if these systems we know are in equilibrium, there should be no net torque. And this is true about any point in the system. So this is sort of a big point to keep in mind. This sum of the torques equal to 0 is true at any point that we choose. So no matter which point we choose, if we add up all of the torques about that point, they had better add up to 0. Otherwise, we would have an angular acceleration about that point, and we know that that means that it is not at rest and it is not in equilibrium. So we want to also impose this, and so then we see that this means we have to choose a pivot point that we'll look at. And in order to choose that pivot point, we'll sort of look at some of the things we want to think about today, but some of that will come with practice, and you'll sort of see which ones will give you more information. So of course, there's no wrong pivot point to choose. We can impose this about every point in the system, but at some point, certain points will lead you to the answer more directly. And so we'll see how that plays out today. So the problem statement for today reads as follows. A 3-meter long, 240 Newton uniform rod at the zoo is held in a horizontal position by two ropes at its ends. The left rope makes an angle of 150 degrees with the rod, and the right rope makes an angle theta with the horizontal. A 90 Newton howler monkey hangs motionless 0.5 meters from the right end of the rod as he carefully studies you. Calculate the tensions in the two ropes and the angle theta. At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have our scenario drawn up here. So we see we have these two cables, which are going to have some tension, and this box here is going to represent the monkey. So what we want to start out with any of these equilibrium problems is we always want to start by redrawing our free body diagram. So I'm going to do that down here. So we will still have the rod, just the same. And now this rope here, we're going to have, this is basically going to give us some tension force, similar over here. So I'll call this T1 and T2. And so we now also can look at our angles. So we're given that this angle here is 150. I am in fact going to rewrite this angle right here as 30 degrees. So that's just to say we know that this is flat right here, so 150 plus 30 is going to give us our 180. So this right here is 30, and this will come in handy when we want to look at this triangle as well as this triangle. Because again, over here we're given that this angle is theta. So just to make the problem parallel, I'm going to go ahead and do that right away. And then we're given, of course, the monkey has some weight. So there's some weight force from the monkey here. And just to keep this clear, this is 0.5 meters away from the edge. And then there's also going to be a weight force from the rod. So in terms of forces, that's really it. We have the tension forces and the weight forces. And so our first step also, we see that there's a couple of angles here. So I would right away just go ahead and break this up into its components. It should sort of be second nature by now. So we basically are going to break this up, which we'll say the x direction will be to the right is positive. And so here we also have T1x And then similarly, we will get the y components. So this is T2y, and then this right here is going to be T1y. So we see again we have these triangles, and so we'll have to work with those a little bit later. But let's first start by recalling the condition that we talked about at the beginning of this video. So we know that this rod is in equilibrium, so it's an extended body in equilibrium. So we know that the sum of our forces must be equal to 0. So this is the first condition, and we're going to impose that on our system. And also let's recall what we're actually looking for is going to be T2, T1, and theta. So these are 3 quantities we want, and we're hoping that our conditions will give us some relation which allows us to solve for these quantities. So we're going to go ahead and break up this sum of the forces into the x and the y direction. So of course our first step, let's go ahead and look at the x. So we see here the only forces acting in the x direction are going to be these forces here, the T2x and T1x. And so if we say the right is positive, we've done this a couple times, this gives us T2x minus T1x is equal to 0. Those are the only 2 forces in the x direction. And so now again, from some trig, we should be able to solve for these. So this T2x should just be equal to T2 cosine of theta. And similarly over here by trig, this T1x should be equal to T1 times cosine of 30 degrees, and this all should be equal to 0. So this is our first equation, and so we can't go anywhere from here, right? So go ahead and look at this, and we see there are 3 unknowns. We don't know any of the tensions, and we don't know the theta. So really, this is good for now, but we're clearly not quite to our answer yet. So for these kinds of problems that make sense, we just have to keep going. So let's go ahead and now look at our y direction. So in this case, we want to look for the forces in the y. And so in the y, we see we have the tension force components, but we also have these weight forces. So we're really going to have 4 forces to worry about, but it's the same idea. So I'm not going to write out this top most general form yet. I'm going to go ahead and say we know what T1y and T2y are. So for instance, T2y should be equal to, let's see, T2 times sine of theta. And then we'll add to that T1y, because that's also pointing up. So that should be T1 sine of 30. And then from this, we want to subtract off these weight forces. So that's just going to be minus the weight of the rod minus the weight of the monkey. And all of this should be equal to 0. So here we have sort of a second relation. And again, if we look at what we don't know, we still don't know T2, theta, or T1. So at this point, it's good to sort of take stock of what we know and what we don't know. And basically, we see we have 2 equations here, and there are 3 unknowns. So for these problems, you always want to be very careful. In mathematical systems, if you have the same number of equations as number of unknowns, you can solve that system. Here we have more unknowns than equations, so we have to do more work to get another equation. For instance, if we have 3 equations and 3 unknowns, we could solve that. In this case, 2 equations and 3 unknowns is not going to get us anywhere. So again, that's not a problem because we also have our second condition, which tells us the sum of the torques is going to be 0 across, about any point that we choose. So now it becomes what's oftentimes the difficult part of these problems, which is choosing a pivot point that we want to force the sum of the torques to be 0 around. So in this case, again, I want to reiterate, this could be chosen as any point in the system. Anywhere we choose, the sum of the torques around that point has to be 0 so that there's no rotation. But one thing we can keep in mind, and in fact, let me write this here. One thing we can keep in mind is that the torque is going to be equal to R cross F. So this is just in general. Torque is defined in this way. And our R vector is going to point from the pivot point we choose to the application of the force. So whichever pivot point we choose, if that is on a force, if it's directly on top of a force, that given force will not give us any torque. So let's see that here. Let's say, I'm going to say for this problem, we will choose right here to be our pivot point. So this pink dot will be our pivot point. And so that means that this force, this tension 2 force, is not going to give us any torque. So it's going to drop out of our relation that we get from this torque. There will be no torque from tension 2 because its R vector is going to be 0. There's no distance between this pivot and the application of the force. So this is something that helps us. Whenever we choose our pivot point, we should choose it along at least one force, or if there's a couple forces acting at the same point, maybe that force. And those forces acting at that point will drop out of our relation, and we'll have a slightly simpler relation here. So in this case, we see the sum of the torques about this pivot point will ignore tension 2, but we will have the weights and tension 1 to deal with. So let's go ahead and say we see that both of the weights will cause this to rotate counterclockwise. And so we will call that let's call that the positive direction for now. Doesn't really matter as long as we're consistent. So the sum of the torques, the torque from the monkey, so let's just write this here, sum of the torques is going to be the torque from the monkey plus the torque from the rod. And then this will be minus, let's do this in general, this will be minus the torque of tension 1, and all of that should be equal to 0. And so again, we've ignored tension 2 because it is on our pivot point. So now we want to break down, solve for these torques, and for the monkey that's straightforward. This is just going to be RF. And let's recall the more general form. This should be really R times F perpendicular. So we see our R vector points in this direction, weight is perpendicular. So this will just be equal to 0.5 times the weight of the monkey. Similarly, our radius right here, that is 1.5 meters away from our pivot, and that'll be the rod, sorry, not the radius, the weight of the rod. And then we have to now look at our final torque. And so recalling that this torque is going to be R times the perpendicular component of F, we see that that perpendicular component we've already solved for, and it's just going to be T1y. So that's to say this really amounts to minus, and then this would be our radius should be equal to 3, because this is acting 3 meters from our pivot point. And then T1 is really T1y. So T1 times sine of 30 degrees. And so all of this, of course, I'll write this over here, all of this should be equal to 0. So right now we see why it was so useful to choose this pivot point. And that's because we don't know this angle theta and we don't know this T2. So that's already two unknowns we've now sort of gotten rid of in this relation. But what we do have is we have T1, and we only have one equation here for T1. We know the weights, so we can actually solve this right here directly for T1. And if you do that, you should get T1 is equal to 270 newtons. So again, follow along in your solutions, but this right here is one equation and one unknown. So it gives us T1. And then for the next part, you should definitely follow along because we now can plug this T1 into these two equations. And then we see we have two equations, two unknowns. So really, we just have a system of equations of which we know how to solve. So if you look at the solutions, it's laid out there. But once we do that, we can solve directly for T2 and theta. And we're given then, or we get then that T2 is 303 newtons. And our theta should be equal to 40 degrees. Okay, so let's go ahead and recap what we've done. We first drew our free body diagram, and then choosing a pivot point at the right edge of the rod allowed us to set the net torque about this point equal to 0 and solve directly for the tension in the left rope. Setting the sum of the forces in x and y equal to 0 allowed us to solve for T2 and theta. Okay, so I hope this video is helpful, and I hope it showed you a little bit of how to approach these problems using our two conditions. So if you guys have any comments on any of these videos, please leave those on the link to the right of the video. Thanks for watching.